All right, welcome to our second lecture. This is the second review of stats. Now, it may not be a review, and that's okay, but it's just the stuff we need to know to be able to do our actual significance tests, find those p-values. Now, I'm going to title this, I think the most important concept in this lecture is the idea of signal and noise. So it's really titled Measures of Central Tendency and Variability. And I'm saying, hey, I'm really talking about signal and noise. Guess what? Our measures of central tendency are our signals, and our measures of variability are our noise. So right here are two visual examples of signal and noise. The example on the left side is a sine curve. This is kind of common in some physiological measures. So you have this sine curve signal, but you also see that in that measure of signal, you see that jagged up and down kind of vacillation, right? Kind of looks like what my lie detector test looked like, right? Like just a calm vacillation there, right? So we can see that the signal would be a pure sine wave, but the noise is the jagged edge, right? That's how it sounds to me. You can even hear that. That's the jagged edge, right? That's your noise. And that noise is affecting your ability to hear me, right? Not too bad. I've just added more noise, right? But the signal is my voice, and the noise is actually my hands rubbing together. You can't hear me as well as you can hear me now. In what we do, our signals are coming from our means, and our noise is coming from having bad validity, reliability, power, right? So whatever we can do to reduce the noise in our data set, we should do because we're increasing our power. So this lecture is really on signal to noise. Let's talk about our signals. Central tendency. Where's the center of your data? How do we get our signals? Well, the mean. The mean is our signal in an experiment. In the things you're doing for this class, the mean is your signal. And you know the mean. It's the average of all numbers in a data set. I am moving on. I'm not going to show you the formula. You know how to calculate this. We are good. But that's our first measure of signal. Now, there are two other measures of signal that are way less common, but are still important to think about. Now, the second measure of central tendency, or signal, is called the mode, and it's the most common score. Notice MO mode, MO most common score in a data set. And these are super simple to calculate. So in the first example, the most common score is 3. In the second example, it's 4. You can see that. In the second example, there's actually 2 modes. The most common scores are 1 and 2. And in the third example, there are 3 modes. Your most common scores are 1, 2, and 3. That's super easy. That's your statistical mode, your most common score. Now, and sorry about that I didn't have the slideshow going up until now, but it's not a huge deal. So there's statistically bimodal and there's practically bimodal. Statistically bimodal means you have 2 equal numbers of most common scores. That is not the case on this slide. This distribution is a grade distribution in a class. Let's say it's my class. And what's important to understand is that when a scientist sees a distribution like this, they are noticing whoa, there's error in my data set, right? There's error there, and I need to figure out what's going on. And 2, they realize, whoa, I have 2 distributions in my one distribution. So I have 2 different humps here. People are responding 2 different ways. Yes, I have one statistical mode of 72. 100 students in my gigantic class scored a 72. That's my mode. But also I'm like, there's 2 humps. This is a practically bimodal distribution. Statistically, it only has 1 mode. So I'm not trying to confuse you. But practically, there's 2 humps here, and the scientific side of me is like, wait, what's going on? There's something going on here. I have 2 different types of responses in my data set. I have 2 different types of people in my data set. So this is an example from a class. If I saw this in a class, which we often do, what do I see here? Well, in my classes, I often see students that do their homework. They are represented by this red distribution right here. And I see students that continue to not do their homework. They don't learn, they don't do so well, and they're thinking at the F level in terms of their own education. So like for in my classes, I'm saying, wait, we have two distributions here. There's two different types of responses. I believe or hypothesize that it's due to their tendency to do their homework. Well, luckily I have all their homework grades, so the scientist in me can look at the scores in my classes and actually see if my hypothesis was correct. Now, I'm going to get rid of all that complicated stuff. You can ignore that if it made no sense. It's cool. What you need to know from this slide is that while this is not technically statistically bimodal, it's practically bimodal. It's telling you that you have two different types of responses in your data set that you're not accounting for. You need to figure out what's causing these two different types of responses so that you can reduce the error in your data set and get a better measure of signal. So when I see something like this, I'm saying, well, hey, I have two different types of responses. I have error here. I don't know why I have two different types of responses. I need to figure this out either statistically by looking at my homework scores or experimentally by designing an experiment, right? But still, I need to develop, maybe I'm wrong, I need to develop more hypotheses. But at the end of the day, when I see something like this, I have error in my data set. I need to figure out where it's coming from. I need to remove it so that I have more power to find a significant result if one exists. Because this is not great for your data. This is two things happening at the same time that I don't know what's going on. I think I know what's going on, but now I have to find out for certain. So when you see something like this, you just go to action. You're like, oh my, I have two different types of responses. What do I do, right? What are my hypotheses? How do I remove this? In my second study, what am I going to do differently? Practically bimodal versus actually bimodal. Median is the middlemost point in terms of the number of observations. So in an odd number data set, it's just your middle score. In this case, we have a data set with 7 observations. So our middle score is 4 because there's 3 observations to the left, 3 observations to the right. If you don't believe me, put your fingers on the leftmost one and the leftmost one, or the rightmost 100. Now move the leftmost one finger in one observation, move the right finger in one observation. Do that until you can't move both fingers anymore, and you will find that 50 is the middlemost score. When you have an even data set, you take the average of the two middlemost scores, which in the first example is the average of 2 and 2, which is 2. In the second example, it's the average of 2 and 3, which is 2.5. 2 plus 3 is 5 divided by 2. So median is the middlemost point in terms of the number of observations. That's it. So those are our 3 measures of signal. And I'm going to tell you this right now. 99% of the time in psychology, we use the mean. And neuroscience, we use the mean. So with that stated, you would probably think, oh, well, that's because the mean must be the best. Well, actually, the mean's not the best in terms of a very common problem that you will have in your own data, and you will have to deal with it. Because if you don't deal with it, you are hurting your signal. Now, let me explain this whole slide. So right here, we have a symmetrical distribution. When we have a symmetrical distribution, like a normal distribution, our mean, median, and mode are all the same. It doesn't matter which one we use. And guess what? For all the statistics that we are going to use in this class, 95% of them assume a normal distribution in your data. So you can see this, we've gotten around this in psychology, in other social sciences, by assuming we have a normal distribution, because it doesn't matter if you use the mean, median, or mode. However, this assumption is often incorrect. And I want to show you what happens when you do not have normal or symmetrical distributions. Let's go to the example on the left. Okay, we're going to assume that the mode is 0, just so that it's a common number line that you're used to. So the mode's 0, right? And we have outliers on the positive side of our number scale. Let's say we have a 1 to 7 happiness score. We have like 5 people that wrote 100 down, and we put them in our data set that way. We didn't know what to do. We just put them in. We just said, whatever. I think they meant 100, so we'll put it on there. Giving up. I'm tired of looking at this data. I'm just going to see what happens with it. I'm making bad choices. It's 3 o'clock in the morning. I'm doing things not correctly, and I made a bad choice. So now I have 3 100s in my data set. Those 3 100s are outliers that shouldn't be there. 9 a.m. Brian can tell you we'll just take those out. We'll have our symmetrical distribution again. But I didn't do that. 3 in the morning, Brian didn't do that. So I have outliers right here. And this picture shows you the impact on your mean, median, and mode. Well, it has no impact on your mode compared to the symmetrical distribution. Right? Sorry about that. The mode just stays the same. It's unaffected by outliers. We don't use the mode. Not going to talk about why. It's complicated. But we don't use the mode, so you don't really have to worry about it. But you can see it's not affected by outliers. What is affected by outliers? Oh, wow. The mean is the most affected by outliers. The mean score changes the most from this point on the number line to this point on the number line. This whole discussion is about signal and noise. And we want to find our true signal. Right here, outliers are making our signal not true anymore. It's having a drastic effect on this mean. And that's a problem. If you have outliers in your data set, you have to get rid of it. That's the practical take-home set of this slide. You cannot have outliers in your data set. You must get rid of them. Now, additionally, outliers have an impact on the median, but it's not as great as that on the mean. But still, in psychology, we use the mean, likely because we make these assumptions of normality, and we don't really think about stats in the way as deeply as statisticians do. So we're like, oh, if we assume normality, then everything's okay. But in your data set, if you have outliers, look at the impact on your mean, median, and mode. They should all be here. That's the true mean, median, and mode. But look, the mode is fine. The mode stays where it is. The median is pulled a little bit towards the outliers, and the mean is pulled a lot towards the outliers. Now, the same case happens when the outliers are on the negative side of the number line. We'll assume this is a 0, and these are negative outliers. Negative 100s, I just put them in. This time at 3 in the morning, I wasn't paying attention. My cat got on my computer and hit the -1, 0, 0, and then just kept copied and pasted. I don't know how. My cat's super smart. You'd be amazed. She can open doors, so I don't know what's going on there. But side note, right? I have these outliers in my data set now. Look at the impact on the mean and median. It's the same. The mean is drastically pulled from the top of the hump. Our estimate of our signal is not true anymore. The same for our median. The estimate of our signal is not true, but less so, right? When you have outliers, you must remove them, particularly if you want to generate an honest signal, a true signal. If we have outliers and we're calculating means, our signal is way off. We need to deal with them. My final piece on this slide is more probably useful in your lab. So when you have outliers on the positive side of your number scale or on the positive side of your frequency distribution, on the right side, if you're thinking mathematically, because I'm thinking like a psychologist. So if you have outliers on the right side of your frequency distribution, you create a tail on the right side. That looks like a tail. It looks like a dinosaur tail, kind of. That definitely looks like a dinosaur tail. So that's how I'm going to remember this. So I've created this tail on the positive side of my distribution. So I have a positive tail. Another word for tail is skew. Positive skewed distribution. Negative tail, I have a dinosaur tail on the left side of my distribution. On the negative side, I have a negative tail. I have a negative skew. You might be asked that in the future. Definitely will be asked that on a Psych GRE or on the ACAT. So I will move on. So I'm done with our measures of our signal. Let's go on to measures of variability. Measures of variability are estimates of noise. That's why we care. And I want you to now imagine a world where there's no error in our data. You can see one day I'm going to be on American Idol. I'm a great singer. But no, imagine a world where there's no error in our data. What would that look like? Well, I'm going to show you. Simple experiment, control an experimental group. Let's look at that control group. All zeros. Everybody scored a 0 in that data set. The mean is 0. The variability in that data set is 0. All the scores are the same. There's no error in our data. There's no variability. In the experimental group, we again have all the same numbers, right? All ones. Our mean is 1 and our variability is 0. Let's extrapolate. When you have no error in your data, you have no variability. When you have error in your data, you have variability. So what are some measures of variability? Our range, smallest to largest number. You know this. We don't use it that much in psychology at all. Not in a way. We might use it to describe our data set if we're really happy with how tight our interval is. But in general, we don't use the range. But you know what it is. So what do we use? I want you to think this out. I want you to go back to 1900, before the 1920s, when we've developed most of these statistics, at least the p-value stuff, but whatever. Just time travel with me. And you understand the concept of signal to noise. You understand the concept of variability, but you don't have a measure for it. So we're in history. We're at the time before we have any measures for variability, and you're just like playing around with numbers. You're sitting there. Maybe it's back further than I'm even thinking. You're on your cave wall, with painting 1, 2, and 3 with blood on the wall, trying to do math because, our ancestors were the smartest cave people ever. So that's great. We're doing that, and we're like, well, I need a measure of variability. What do I want to know? That's a good question. I'm creating a measure of variability to capture noise. What's going to be my first step? Well, for me, I understand the mean as well. We've already calculated the mean. We know that. I don't have to create that. That's been known forever. That was handed to us with the 10 Commandments. The 10 Commandments plus how to calculate the mean. That's how we got it. That's a joke. I'm just kidding. But we know the mean, and we're like, okay, I want to create a measure of variability. Well, I want to know, on average, how much these scores vary from the mean. I'm like, well, I know a mean. I know how to calculate means. So let me calculate the mean of deviations from the mean, or the average deviation from. Let me see what's going to go on there. So first thing I got is my data set, 1, 2, and 3. What's my mean of that data set? Well, 1 plus 2 is 3 plus 3 is 6 divided by 3 is 2. My mean is 2. And I'm like, well, I want to know on average how much my scores in my data set deviate from the mean. So I'm like, okay, 1 minus 2 equals -1. That first score deviates from the mean by -1 units. 2 minus 2 equals 0. There's no deviation. 3 minus 2 equals 1. There's a positive deviation from the mean. That third number is a little bit greater than the mean. So I'm like, okay, I'm going to calculate the average. So the first step I do is I take -1 plus 0 plus 1. That equals 0 divided by 3 equals 0. Yay, I have no variability in my data set. Wait, no, all these numbers aren't the same. Ooh, this doesn't, what's going on here? It adds to 0. Why is it doing that? Oh, because with the mean, all the numbers below the mean will have a negative deviation score. All the numbers above the mean will have a positive deviation score. They will always add to 0. Let me test that. 1, 2, 3, 4. Oh my, it works here. It works in the 1, 2, 3, 4 example as well. Oh no, what do I do, right? Why is this happening? Mathematically, we know why it's happening. Mathematically, I'm like, I have these negative numbers and positive numbers, right? So, I'm like, well, let's just get rid of the negative numbers. It deviates from the mean by -1. Let's just take the absolute value of all our deviations so we can look at this. That's what would make sense, right? And in that case, I'm like, I have 3 numbers. I have a 1. First number deviates from the mean by 1 in terms of absolute units. The second number is 0. The third number, 1. And I'm like, okay, so 2 out of 3. On average, my scores deviate from the mean by 0.67. Now, that's one potential solution using the absolute value. Unfortunately, that's not the solution we chose. We chose to square each score, average each squared score to add each squared score together, find the average of those squared scores, and then take the squared root. We call this standard deviation. So to me, it's the illogical response. It's the illogical equation, but it's the one we use. I honestly, conceptually, understand variability better when I'm using the absolute value of those deviation scores. But that's not what we do. We've decided to solve the -1 problem by squaring, summing, averaging, and square rooting. Let's see that in action. Now, I believe taking the absolute value would have been the smart solution, but that's not what we do. We do the thing I just described. So let's go back to that 1, 2, 3 data set, and let's use the new solution, not the absolute deviation. Let's square those deviation scores and do all that math. So our first step, calculate our deviation scores. We know our mean, 1, 2, and 3. We know our mean is 2. We know that from before. We know our deviation scores are -1, 0, and 1. We know that from before. So I'm going to square each of those. My first step is to square those deviation scores to get rid of that negative sign. 1, 0, 1. Those are my new deviation scores. I add those together. 1 plus 0 plus 1 equals 2. That's really important. That is a statistic called sum of squares. Sum of the square deviation scores. All I did was square my deviation scores and sum them together. Now, I'm going to stop here for a second because this is the foundation of our F statistic that we will use later on. So I really need you to understand what sum of squares is. It's literally just the sum of the squared deviation scores. And it's the foundation of some very important statistics we use in this class. So keep that in mind. But we're not at the end of our calculation yet, right? We're trying to calculate the approximation of the average deviation. And we're doing this weird squared square rooting process. So right now we've just squared them. We've added them together. Now we divide by 3 the number of observations. And so we get what is known as our variance, S squared, the average of the squared deviation scores, right? And that equals 0.67. And then finally, we get our standard deviation by taking the square root of our variance. Notice the symbols here, S and S squared. Variance is just standard deviation squared. Standard deviation is just the square root of variance. In this case, it equals 0.82. Now, this matters. This is our approximation of the average deviation score, of the average deviation, with the understanding that the average deviation always adds to 0. So in terms of signal and noise, standard deviation is noise. And pretty much every one of our statistics that we use either sum of squares, variance, or standard deviation. Everything we use uses one of these numbers for the most part. So that's it. That's how we got to the standard deviation. Average deviation score is always added to 0. And our standard, so we do this approximation, the standard deviation. It's our best approximation of the average deviation score. It's basically the same thing. The math works out a little differently, but conceptually, our standard deviation is our approximation of the average deviation score, knowing that the average deviation score is always summed to 0. So I want to point something out. The statistical packages you use, not Excel, but everything else, assumes that your data is a sample from a population. There were some math theorists along the way that showed that if we just divide by n, we are underestimating the size of our standard deviation when we take a sample from a population. So what we have to do is these statistical programs adjust our n minus, they take 1 off our n. That'll make our standard deviations larger, right? If you think about it this way, 5 divided by a standard deviation of 2 is 2.5. 5 divided by a standard deviation of 2 minus 1, which is 1, is a standard deviation of 5, right? So I just want you to know that the packages, when they calculate standard deviation, do so in a way where they don't use n, they use n minus 1. And that's what we will use in the future, but n minus 1 doesn't make any conceptual sense. Now you know where standard deviation came from. We discovered a statistical problem with it, that it was that measure was overestimating, it was actually underestimating our population standard deviation, so we just kind of reduce n by 1 to make everything better. I just want you to know this. What you need to know from this slide is just that the statistical packages use a slightly different formula, but conceptually, it's the average deviation from the mean. It's our approximation of that, with the understanding that the average deviation from the mean always equals 0. So here's a practical thought problem for us. We've run our experiment. You can replace the conditions with conditions from your experiment. We have the standard deviation of one condition is 5, and the standard deviation of another condition is 2. What have we learned about our experiment? Well, in this case, we've learned that something in that second condition is making scores more consistent. Well, that's important the way I set it up, because in the way I set it up, that's my experimental condition. That's me adding the thing that I think will affect behavior. And when I add that thing, people respond more similarly than in the control condition. I'm not a fan of this. This is a bad sign. I'm like, oh my Lord, no. My standard deviation is twice the size of my control condition than my experimental condition. I need to figure out why, right? Not only is this my estimate of noise, but I'm looking at it across my two conditions. I'm like, oh my Lord, no. Because another assumption we make when we use the statistics is that the standard deviations, the variance, is the same across all the different levels of our conditions. That's not the case here. Well, why might that not be the case? This is where we have to start hypothesizing what's creating the error so that we can remove it. Well, in this case, control versus experimental condition, my control condition has a very high variability. I'm betting I can give my instructions a better way. It appears that my instructions in the control condition might be being interpreted vastly differently. So one thing I'll do if I see something like this is now I'm going to provide a video recording of the instructions. Maybe it's a video of me doing the test. I don't know what level I have to go to for my participants, but I don't care because statistically there's a problem in my control condition compared to my experimental condition. Right? That's one way I'm looking at this. I'm like, ooh, what did I do? Maybe I worded my instructions poorly. Very common in my experiments, right? Maybe I did something like that. I need to figure out what's going on there to more than double the size of my noise in that condition. Because that's not good. I don't want to have one condition with more noise than the other condition. Because as we saw earlier, when you have more noise, that impacts your estimate of signal as well. So yay, right? Or, let's say I look at everything, I can't find anything wrong. The instructions were great. I ran experiments to see if people could understand them, right? Like I was just testing everything I could. And then I'm back to my experimental condition. I'm like, wait, maybe my experimental condition was just really good. And my experimental condition got everybody to think the same way, more so than participants in my control condition who don't naturally think the same way. So in that case, this difference and this variability is important and is something I can report. Maybe I didn't affect the means in these two conditions. Let's just assume that the means were identical, but the variability was different. People got closer to the mean. That's an important effect. If you can make a group of people act more similarly, you're going to have less disagreement. If you can do this and you're a politician, you can get people to vote for you. I mean, there's some importance here trying to figure out, what happened in this experimental condition to make people act the same way. That's an important practical finding. So I've been talking about signal and noise for quite a bit. And we come to my favorite statistic in the whole world, Cohen's d. Cohen's d is just a ratio of signal to noise. And the signals in a simple experiment, control versus experimental condition, right? That's one independent variable, but control versus experimental condition, one independent variable. My signal is the mean difference, right? I want to know how much my experimental condition differs from my control condition in terms of mean. That's my signal divided by my estimate of noise, which is standard deviation. Technically, I do want to mention that the mean differences are also measuring noise as well. So it's signal plus noise over noise. So this is my favorite statistic because it requires no assumptions, no p-values, but we can interpret it. You can understand it. It's technically a descriptive statistic, which is really cool. Now, in order to do this calculation, you have to choose which standard deviation. Now, you can do a normal average of both your standard deviations when you have equal n. So I can take the standard deviation from my control group and average it together with the standard deviation for my experimental group and use that as my denominator in the Cohen's d calculation. Or I can use a weighted average, which I'll explain at the end of this slide, which is when you have an unequal n. Or some people actually argue to just use the control group. Let's take my previous example where my experimental group got less variable because my experimental condition reduced variability. This is going to be a common problem in experimental conditions. If your control condition is a do whatever you want condition and your experimental condition is do this one thing, you're going to have less variability in your experimental condition. So you're actually, that's all due to your experiment, your design. So really, it might be best just to use the control condition. Now, there's no single right answer here. You just need to be able to defend your answers statistically. Because there are more than one correct answer in statistics. Not everybody agrees on what to do here. I myself, I am an averager. I will average my two standard deviations together. But some people are going to use the control group, especially when they're using pure control groups. And some people can't use a control group because you have things like happiness and sadness as your two levels, right? There's no control group there. So whatever you use as your denominator, it doesn't matter. It just matters that you argue and that you understand that a measure of standard deviation is in your denominator. Okay, you can tell I have fun with stats. I really enjoy it. I really think about it a lot. But you don't have to think about this that much. I'm going to go back and leave that last part out. Signal to noise ratio, mean difference over some estimate of standard deviation. That's your Cohen's d. Now, whenever you're doing division, you have to think about what's going on here. So essentially, we're converting our mean difference to a standard deviation difference. We're saying we have this mean difference. It's in our numerator. We're dividing it by our standard deviation. So what we are doing is we're converting that numerator, that mean difference in units. It could be happiness units, could be attention units, could be units of concentration, could be units of intelligence. I don't know what your studies have in them, but it's just whatever units you're looking at, emotion, recognition, all the stuff we talked about the other day. Now, when we have that difference divided by a standard deviation, we are converting that mean difference to standard deviations. So let me just give you some examples. Our Cohen Ds of 1, this tells you two things. The two means are one standard deviation apart, different, or separated. That's what I was trying to say earlier. And it tells you signal, in this case, equals your noise. Your mean difference equals your standard deviation. Your signal equals your noise. Let's do another example. Cohen's d equals 0.5. Right? This is your proportion of your signal to your noise. So if you understand proportions, you know that your signal is half the size of your noise. I do not know why they say equal there. It should say equal to... Your signal is half the size of your noise. Well, the great thing is that I can change it. Your signal is half the size of your noise. All right, so now I fixed that. I'm going to restate it. When your Cohen's d is 0.5, your signal is half the size of your noise. We can see that from the proportion right there. Your signal is half the size of your noise. Your two means are half a standard deviation apart, different, or separated, and your signal is half the size of your noise. In psychology, Cohen's d has 3 different interpretations. Small is 0.2, that's basically nothing. Medium is 0.5, that's there's something there. And large is 0.8, there's something massive there. So when our Cohen's d equals 0.2, it's small, 0.5, it's medium, 0.8, it's large. Now in physics, they have Cohen's d as well. They don't call it that. They call it sigma. So if you have a 3 sigma, a Cohen's d of 3 in physics, you have what they would call what we would call a medium effect, and they would say there's some evidence, but I'm not sure if I've discovered anything. But if they have a 5 sigma, a Cohen's d of 5 in physics, they say they've discovered something. Now, this is important, right? Because not all Cohen's d's are interpreted the same way, even in psychology. You might have a small Cohen's d in something. Let's say you're a clinician, and there's an impact that reduces suicidality by a small Cohen's d. But when we do the math on the population, we see that small practice saves 10,000 lives a year. That's nothing to say that's nothing to laugh about. That's nothing to say that's let me pause. I got too excited. That is important, right? So you do have to think about what a Cohen's d means, where it fits in, what's the interpretation. But for today's discussion, remember, this is my favorite statistic. So let me just give you the quick final summary. It's a signal to noise ratio that tells you how many standard deviations apart the two means are. So if you look at a Cohen's d of 1, your two means are 1 standard deviation apart, your signal is equal to your noise. If your Cohen's d is 0.5, your two means are half a standard deviation apart, and your signal is half the size of the noise. So I told you I was going to show you how to calculate a weighted average. So here's an example where I have 2 averages. The first one's 2, the second one's 1. They can be, let's just say they're standard deviations. So my estimate of standard deviation is 2 in the first example and 1 in the second example. But I want to average these together, and I could just take 2 plus 1 divided by 2, get 1.5. But what I'm not accounting for is the fact that I have twice as many observations that average to 1 as I do that average to 2. So what I need to do is I need to bias this average in favor of the group with more observations, right? Because it's unfair to average together 2 and 1 directly when you only have half as many observations in the first data set as you do in the second data set. So the simplest way to think about it is, I don't have an average of 2 here. I have 5 2s. 1, 2, 3, 4, 5. And I don't have an average of 1. I have 10 1s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You add those together, divide by the total number of observations, 15. So you get 20 over 15. If you get this, an easier algorithm to think about this is I have 5 observations that equal 2 times 5, plus 10 observations that equal 1 times 10, divided by the total number of observations, 15. This weighted average is how you calculate your GPA math as well. So I think that would be a good way for you to just sort of figure out the weighted average. But let's say, you have a lab and a class, right? You have an A in the class and you have a B in the lab, right? So your A in the class is worth 4, and that's worth 3 credits. Your B in the lab is worth a 3, and that's worth 1 credit. So we got 4 times 3, we got a 4.0 for an A, times 3 credits equals 12, plus 3.0 for a B times 1 credit is 3. 12 plus 3 is 15, right? We have 15 divided by 4. So we have 15 total GPA points divided by 4 credits. and that's a weighted average. And then I'm pulling out a calculator behind the scenes here. Got to find it on my phone real quick because I want this to be right. So we have 15 GPA credits with weighted averages, right? 4 times 3 is 12, plus 3 times 1 is 15, divided by 4 total credits equals a 375. So if you get a B in your lab and an A in the class, together the GPA for that whole section is a 375. That's what weighted averages are useful for that. So, okay, let's talk calculations. Now I have 3 stats programs. Well, I have more than that, but I have 3 stats programs I'm going to show you on my computer right now. The first one is Excel because you can do anything in Excel, and you should do your problem set in Excel. But I'm going to show you how to do everything I've just done in Excel. But I want to point out that SPSS and PSPP use a special formula where instead of n in the standard deviation, you got sums of squares divided by n, they use n minus 1. So in their formula, they replace n with n minus 1. There's a reason for this. I'll talk about that reason in our next 2 lectures. But right now, I just want you to know that this is happening. So if you use PSPP and SPSS in Excel right now, you're going to get different calculations for your standard deviation. But the reason for that, it's just statistical reasoning that I don't want you to think about right now. What I want you to think about in terms of the calculations I'm going to have you do is what is the standard deviation? I need you to know that the standard deviation is the approximation of the average deviation, given the fact that the average deviation is always 0. Now, because it's an approximation, you can tweak the formula, and along the way, we've tweaked the formula from n to n minus 1. But that doesn't help you conceptually. I want you to know conceptually why you're doing this. So today, you should use Excel, because it'll make sense. But I'll show you how to get all the answers in Excel, okay? So I'm going to go through these 3 programs. Right now I'm pulling up Excel, and I'm just going to go through how to use it. See, I've already done it, and I just want to show you how to make this all work. So first thing I need to know is my mean. So in Excel, if you hit the equal sign in the cell, you can then type in a formula. Well, the formula for mean is average, right? Equals average. You click on it, and then you just highlight those 3 numbers. My average is 2. Equals median. I highlight these numbers. My median is 2. And I'm going to get no mode, but that's okay. It won't give you a mode unless there's more than 2 numbers. So right now it's going to say NA, but watch what happens if I change it to 2, right? But our number set is 1, 2, and 3 from before. So our deviation scores, this is some useful stuff. So our deviation score equals our score minus our mean. Now, in some situations, I would click on our mean. But for this situation, I'm just going to type it in, and I'll show you why in a second. But you could click on that box where the mean is and get your mean. But equals this cell minus 2. That equals -1. And then you're like, oh, I got to do that 2 more times. No, you don't. You just drag. Did you see? Go back and look at what I did. I reached up here and I dragged it down. I dragged it down. You can see, right? That's doing the math as well. It's taking nothing minus 2. Okay, so that's why I put it in there has a 2 so that it would just I could do this drag and drop thing. So now I'm like, I got my deviation scores, and then I need to square them to get rid of the negative signs. That equals this times this, right? That's squaring. You could do it other ways. You could put other things in there, but you can also just do that again, and now it squares everything. And now my sum of squares, that equals the sum of all of these. My variance is the average of my sum of squares. So that equals my sum of squares divided by the number of observations, which is 3. And then this equals the square root. Your standard deviation equals the square root of your variance, as I described before, right? Or, and that's just going through the steps, or with Excel, standard deviation of the population equals that, or standard deviation, which is assuming a sample from a population, which is the n-1, equals that. So you can see I have the exact same number for the population calculation. That's what I have taught you because that makes sense. This is that, remember I said this is what happens when they change n to be n-1. So if I just say this equals this divided by n-1, 3 minus 1 is 2, equals that. And then my standard deviation equals the square root of 1, which is 1. So that's where the numbers come from. Excel is great for every single calculation we've done. I'm not going to post this online just yet, this Excel file, because I want you to get used to clicking equals and all that. Some of my students have never used Excel before. If you struggle and you're losing it, shoot me an email. I'll send you the file. You'll be able to do all your calculations for this problem. Okay, but the problem I'll show you in a second. But this is how you do it in Excel. All right. Now I'm going to SPSS. I've already typed in my data set 1, 2, 3, which is what I call it. Analyze. Descriptive statistics. Descriptives. What are my options here? We got the mean, we got the standard deviation, we got the variance. Click continue. So I'm going to get some of the ones I want. I'm not a huge fan of SPSS for things like this, but that's okay. Right? You can see my mean is 2, my standard deviation 1, my variance is 1. So they're using that assumption of sample from a population. You actually can't make SPSS do the population calculation easily. You have to basically go in and write computer code to make that happen. So then analyze reports, case summaries. This is another way to get statistics. If you have a grouping variable, this is where you can get statistics for your control and your experimental groups by throwing your grouping variables down there. And then I can click all my statistics options. Mean, number of cases, fine. That's n. I want my mean. I want my median. I want my, nope, standard deviation. I want my variance, right? You have other things in here that are important. Kurtosis, that's a measure of normality. Skewedness is a measure of outliers. So you have some interesting stuff in here, okay? But now with the reports and summarized cases, I can get all of the statistics that I want, and you can see that they're all those population statistics. Mean, median. The one thing it doesn't give me is mode. Nobody uses the mode anyways, so we're not going to worry about mode in the statistical packages that aren't Excel. Maybe I missed it though, so I'm going to look. I don't use Excel that much. It's been years, but I know you all do, so I just want to see if I missed mode. Nope. Cancel. Okay. So then I'm like, I do know a way to get mode. Graphs. I like the legacy. You can build it whatever. Legacy builder. I just want to go histogram here. Nah, I'm actually going to cancel this. I'm not going to show you that. We'll show you that later when it makes more sense. But this is how you use SPSS to get everything except for mode. Mode, you can just count your data. You'll be fine with that one. Now, SPSS costs a lot of money. No, I'm good. I don't need to say that. You probably would. SPSS costs a lot of money, and those of us that kind of work in the Linux world a little bit, we make our own programs and whatnot. And somebody in that world made a program called PSPP, which is SPSS flipped, right? You can download that program. I have a video on my YouTube page about how to download that program, but it's essentially exactly like SPSS. I create a variable, data 1, 2, 2, 3, click on my... Okay, so because it's free, it's not as nice as SPSS. I have to hit enter to make it work, right? SPSS would just automatically do that. Small little differences here, but look, the top looks very similar. Analyze, descriptive statistics. You can see I don't have all the choices, but I got frequencies, descriptives. I can get my descriptives like I did before. Ooh, I'm gonna make this bigger because it might actually be better. So now I'm on PSPP, mean, standard deviation. I don't like those. I don't want any of, I do want variance. Yes, I do. I click this number into here. I click OK. And then I wait for ever. Oh, it's up here. I'm like, where did my data go? So, it's a free program. So sometimes with free programs, you got to deal with stuff. Let me see here. Where did it go? I still can't find it. Where is it? Where are you? I bet you it's on another page or something here. Where would it be? Should have played around with this a little bit more. Oh no, it should be in here. Okay. There we go. Oh no. Oh, I put no data. Oh, Brian. Brian put no data in. Don't do that. 1, enter. 2, enter. 3, enter. All right. Now we go analyze, descriptive statistics, descriptives. Everything's clicked. I click OK. And then there you go. My mean, standard deviation, and variance. Like I said, sorry that it was a little choppy. I'm not perfect. But these are the programs that you can use. And this one's free to download. I'll help you download it if you come by my office. And then I want to see if the other aspects in there, descriptive statistics, I want to go to frequencies, variance, skewness, range, mode, median. So this one's actually even better than SPSS because it gives me the mode and median. So now the same thing. And you can see it's the exact same button presses. Our mean, there is no mode, just like in Excel, right? Standard deviation is 1, variance is 1, the minimum's 1. I should have got rid of the range, whatever. And the percentiles doesn't matter. But essentially, you can see that you can use stats programs to do all these calculations for you. I never want you to struggle with calculations ever again in your life. So now let me head back to this specific PowerPoint and go to what you should be able to do. Calculate mean, median, mode, range, deviation scores, sum of square deviation scores, variance, standard deviation, and Cohen's d. I'll talk about Cohen's d in a second, how to calculate that. There's no clicky box program that calculates Cohen's d. You always have to do it by hand. So you just take any mean difference and do it by hand. Okay. Understand that the mean, median, and mode are all measures of central tendency, and they are a signal. Conversely, even though it's not on here, you should know that measures of standard deviation are noise, which is important. I don't know why I don't have it on here, but that's fine. I want you to be able to describe why standard deviation is an approximation of the average deviation, while also knowing the average deviation is always 0. So basically, I want you to say, oh, well, we have equal number of negatives and positives when we have the deviations from the mean. So we square them to get rid of the negative sign. We add those squares together. We take the average of those And then we square root to get rid of the squared, and those are your 4 steps of standard deviation. This is our best approximation of the average deviation, but the average deviation always equals 0. Describe Cohen's d in terms of standard deviation and in terms of signal to noise ratio. So standard deviations, the number of standard deviations your 2 means are different. Signal to noise ratio, it's the proportion. Your Cohen's d is 1, signal equals noise, Cohen's d is 0.5, signal's half the size of your noise. And also go back to that and reflect on signal and noise in our field versus signal and noise in physics. We have people are drastically different. Particles are very similar. We have different rules for what's significant, what's important. And in fact, in physics, while we don't call Cohen's d significance, they do. They say it's important and significant. So here's your problem. Analyze this data set using all measures of central tendency, mean, median, and mode. Go through every step of the standard deviation calculation. So use Excel the way I did, making sure you're telling me why each step is getting you closer to an approximation of the average deviation. So you would say, oh, I want to know how much scores deviate from the mean, so I calculate deviation scores. I do something to them to get rid of the negative sign. I then do something to them, I do something else, and I do something else, and now I have this approximation. I'm not going to tell you the answers on the problems while I'm explaining the problem, so be clear there. Calculate Cohen's d using one method of your choice. Use Excel, mean 1 minus mean 2 divided by standard deviation. Feel free to just use the control condition, but give me a reason why you're using that control condition. You still will have to do that. So the easier calculation is just to divide by the standard deviation of the control condition, but you've got to give me a reason why you think that's a good case in this example. Hint, it is actually a good case in this example. Then I want you to just make any 3 observations about this data after you do this analysis. So I'm literally looking for just 3 correct statistical observations for you. What signal? Noise. Right there is 3 observations if you think about it. Signal, noise. You have two estimates of noise, 1 true estimate of signal, by the way, but it's going to be super easy. I just want you to think about the data. I know that some of my students think stats, correct answers, but I need you to understand that while that's partially the case, you get to make choices, like in this Cohen's d calculation. All right. So let me go over the example. Humans have a meaning-making psychological process that becomes activated when confused. That's actually a theory. It's called the meaning maintenance model. Steve Hines' work. I love it. So I've designed an experiment based off that model. And in their experiments, one of their manipulations is they confuse participants by having them read Kafka. So in this Kafka story, it's really hilarious, but essentially you have a boy turns into a cockroach, and his parents are punishing him for being a cockroach, and they think, but they're not acknowledging that he is a cockroach. So it's like, why are you under your bed? I'm going to hit you. You shouldn't be under your bed. I'm going to punish you. It's a weird story that makes no sense at all. That's why I'm not even going to try to describe it. But imagine that, right? Told in a story with lots and lots of paragraphs. That is very confusing versus a control story where they read about a normal boy in their normal life that's not a cockroach. Then they have participants solve all these different, in their real research, all these different kinds of puzzles. So I just put this in the context of a puzzle that you've taken. You remember on standardized tests how you get like a couple symbols and you have to predict the next one in the list? Well, they did a whole bunch of those questions. And we measured the time to solve their puzzles, okay? And the results in the control condition are these numbers. The results in the confusing conditions are these numbers. Calculate the mean, median, and mode. Calculate the mean, median, and mode. Calculate standard deviation. Calculate standard deviation. Calculate Cohen's d. Give me 3 observations from this data set. Shouldn't be too hard. You have the stats packages now. You can use Excel. We get Excel for free if you go to, I can actually just show you that. So if you just go Office 365 and log in with your Regis credentials, I'm already logged in. If you click up here, you can install, by clicking this button right here, you can install all these programs onto your computer. So enjoy. You can install Excel. Okay, with that, how do you get there from the Regis's website? Fine, insight.regis.edu. Oh, okay, great. Regis.insight.edu. Maybe it's not open. Definitely not there anymore. That's fine. Office 365, where you get your email, just look at the top of that, okay? But that is the end of this lecture. I'm sorry I got a little rambly at the end and in the middle there. If anything doesn't make any sense, text me. You have my number. My office hours are Tuesday from 11 to 3. That's a big chunk. I'll spend that whole time with you. I'm around. Thursdays I kind of stay at home. It's Thursday right now. I'm at home. Fridays I come in and I do research. You can come talk to me for a little bit, but I'll kick you out. Mondays, I have our class. You can meet me after for sure. Wednesdays, I have our class in Capstone, so I'm on campus for the whole day, but I'm just kind of chilling. Tuesdays are kind of like Thursdays. Okay, but I'm more likely to be around. Well, yeah, my office hours on Tuesday, so I'm around a little bit more on Tuesday. So perfect. And go to your Office 365 and download all your Microsoft products for free. So I am sorry that this went a little bit longer than I wanted it to, but that is life.